Hello, my name is Jaclyn Champagne. I am a finishing grad student at the University of Texas at Austin, where I've worked primarily with Caitlin Casey. So I'm excited to talk to you today in preparation for the Quasars and Galaxies Across Cosmic Time conference. This is the longer recorded version of the talk, but I will be presenting a shortened version on Thursday of the conference. So I will be presenting a series of studies I have led, searching for enhanced galaxy evolution in the environments of redshift 6 to 7 quasars. So this has encompassed both my master's thesis and a current project that I am working on now. My master's thesis was in collaboration with some folks from MPIA, and now I am also working with some people from UT on these projects. I'm finding it very strange to record a talk ahead of time, so forgive the awkwardness, but let's get right into it. So some cosmological context for why quasars are particularly important objects for looking for early signs of clustering. There are a couple of concepts that we should keep in mind from lambda CDM. So the first is hierarchical collapse. The largest structures accrete their mass through smaller objects. So that means larger structures later. But also with cosmic downsizing, we see accelerated growth at early times. So the largest structures will also grow the fastest. So in these dense regions of the cosmic web, we will see the evolution and accretion of dark matter halos happen faster than in less dense regions of the cosmic web. So I'm illustrating that here with the Millennium simulation. So this is dark matter only. Looking at very, very high redshift, we are already seeing imprints of the cosmic web. So we are seeing these dense filaments, and the voids will start to become apparent. And we see the largest gravitationally bound structures forming at the centers of these very dense knots. So by the time we get to redshift 1, redshift 0, we are seeing galaxy clusters form in these super dense regions. But again, at redshift 6, we can already see those very wide scale filaments. So I am most interested in finding protoclusters in the very early universe. So galaxy clusters are structures that we find ubiquitously in the present day universe out to redshift maybe 1.5. They're fairly homogeneous structures bound to a dark matter halo with masses ranging from 10 to the 14 to the 15 solar masses. The definition of protocluster is more debated in the literature, but the least controversial way to say it is that it's an unvirialized filamentary network of galaxies that are, loosely associated. They're expected to collapse into probably one dark matter halo that is gravitationally bound before redshift 0. So how do we connect what we know about dark matter halo assembly with the baryonic characteristics of galaxy clusters? Again, from a dark matter perspective, we're seeing on the right 3 protoclusters of varying masses, the most massive down to the least massive, and then going from redshift 2 to the present day. The most massive structures are very extended up to 0.5 degree on the sky at early times, and all of them are going to collapse to a tight virial radius by the present day. So we should be looking for structures that are very extended. And then the predictions of star formation within protoclusters, we know from simulations that protoclusters would have occupied between 1 and 5% of the total cosmic volume at redshifts greater than 2. But in practice, we don't have very good volume constraints on individual systems, usually due to spectroscopic incompleteness. At various times, they're predicted to have contributed between 10 and 30% of the total cosmic star formation rate density. So between redshifts 2 and 6, incorporating the information that we know that they should be very extended and that they should be contributing non-negligibly to the total cosmic star formation rate density, it makes sense that we should see peaks in star formation across megaparsec scales at high redshift. So how do we identify protoclusters in the redshift greater than 1 universe? If we are just blindly looking for these objects, it makes the most sense to identify them as overdensities of star-forming galaxies. So massive galaxies are a good place to look for nearby protoclusters. They are already residing in massive halos, and so it is likely that we should find overdensities of galaxies that are actively evolving nearby. So that has historically included massive radio galaxies as well as quasar host galaxies. They've also been found serendipitously upon spectroscopic follow-up of certain galaxies like Lyman alpha emitters, H alpha emitters, or dusty star-forming galaxies. And sometimes serendipitously, we just see a peak in that redshift distribution. So the main methods of finding them has been through targeted narrowband imaging, or they're found in these wide field narrowband imaging surveys, or follow-ups of unresolved sources that might have come from Herschel or Scuba 2. The schematic here that I'm showing is from a protocluster review paper that is already a few years old. And so there are more spectroscopically confirmed protoclusters that we know of now, but we know that they are fairly rare objects in the early universe. So they're already pretty hard to find. This is coming from another protocluster paper that suggests a possible evolutionary scenario for these objects. And so we know that there should be a growing phase at very high redshifts, where massive galaxy formation is going on in these sort of separate halos along these filaments, where cold gas accretion is still possible. And by redshift 2 or so, we should see AGN feedback turning on and the rise of red massive galaxies, possibly quiescent galaxies already. And by the declining phase, we should see those classical features of galaxy clusters with these red dead massive ellipticals. But I'm most interested in these early times where we should be finding overdensities of star-forming galaxies. And this brings us to the Quasar Revolution that has already been going on for 20 plus years. But starting in the early 2000s, the spectroscopic and narrowband discoveries of rare radio loud quasars in surveys like SDSS, totally expanded our sample of available quasars to start looking for overdensities and learn about their environments. So this is one of the early redshift 5 quasars that were found. And then early studies looking into the environments found filamentary clustering of Lyman alpha emitters and Lyman break galaxies around these quasars. Similar searches for red massive galaxies also found overdensities of 5 to 10 times what was expected for the field. So we already know that there is some evidence to support the fact that massive galaxies have enhanced evolution around these quasars. And there is also a strong clustering between LBGs and quasars using the angular correlation function. So there's a strong cross correlation between quasars and LBGs, specifically around redshift 3 to 4 in this particular study. And the autocorrelation length of LBG pairs is 4 times higher than what was measured in random fields. So we can probably extrapolate this. If LBGs and QSOs, quasar host galaxies, trace the same underlying dark matter, we would expect this trend to continue out to redshift 6. We would just naively assume that. So coming to a specific sample of quasars that I've been working on for some time, this was, a fairly groundbreaking discovery in these redshift 6 to 7 quasars at the end of reionization, suggesting indeed enhanced galaxy evolution very close in. So DeCarli et al. 2017 found an overdensity of C+ emitters less than 100 kiloparsecs away from these extremely bright quasars using ALMA. And this suggests enhanced star formation less than a gigayear after the Big Bang. And this represented a 10 times overdensity above the C+ luminosity function at this redshift. So for my master's thesis, I led a complementary search using the continuum data for these quasars. So there was a total set of 35 quasars between redshift 6 and 7, where we were again looking for enhanced obscured star formation. So coming just to the continuum data, dusty star forming galaxies are rare enough that we would expect less than one source per ALMA primary beam. And so continuum overdensities, if we find multiple continuum sources in the field of all of these quasars, that might indicate enhanced star formation in the form of dust obscured galaxies. So this is ALMA band 6 imaging. And I am showing the 4 quasars that were from the original Nature paper showing the C+ overdensities, so a subset of these 35 quasars. So I'm showing the quasars themselves actually masked out. where the circles are indicating our continuum identified sources, and the squares are the C plus emitters from the DeCarli paper. And only one of them lines up with a spectroscopically confirmed source. And interestingly, we don't really see continuum in the other C plus emitters. So my paper concluded that there was no average millimeter flux continuum over density, showing sorry, pardon me, we found no average continuum over density when averaging over all 35 fields. So blank submillimeter and millimeter number counts are pretty well constrained with interferometers and single dish observations. But of course, by design, they do not encode redshifts. We are just counting the number of sources on the sky as a function of flux. And so in 12 of the 35 fields, we found a total of 15 sources. Only one of them corresponded to a spectroscopic redshift from C+. So that's interesting. That wasn't necessarily what we expected. So what are the possible explanations for that? So just showing a little schematic here of what it might look like to look at a Redshift 6 protocluster. We see that there are a number of effects at play. So first of all, we're looking really far out. So there might be some low redshift interlopers. These are also going to be very spatially extended, like I said in the beginning. And so it's possible that in one pointing, you're not finding the full extent of these filaments, or perhaps you just happen to be pointed away from the densest parts of the overdensity. And so you may lose this signal. So the survey, the observational limits that we have, it was a fairly small sample of quasars, just amounting to a small total area for cosmic variance statistics. We would definitely want more quasars or larger areas around the quasars to kind of get around that. We have a small field of view with ALMA. So this is only imaging the inner like 100 to 150 kiloparsecs at redshift 6. Like I said, these are going to be megaparsec scale over densities. So that is definitely a drawback there. But the biggest thing is the very large redshift slice that we're looking through because we don't have redshifts for any of the sources. And because of the strong negative K correction for millimeter flux, we know that sources are going to have pretty similar flux densities from redshift 1 to n. And so it's very hard to kind of immediately filter out low redshift interlopers at 1 millimeter. There are a couple of physical explanations, though. There could just be a dearth of dust emitters in the early universe. If the main star formation mode is not through these extreme dust obscured galaxies, then we wouldn't find them in dust continuum, of course. If quasar feedback is an important role here, within the inner 100 kiloparsecs, that could be suppressing star formation in the very inner regions, again suggesting that we should look a little wider out. Or quasars don't sit at the virial center of the overdensity. Again, if we're pointed away from the densest knots of these filaments, then maybe that quasar is just embedded in a different region where the overdensity signal is not as strong. So a different study that I am now working on is looking for a different population of galaxies in these same fields. So by looking for Lyman break galaxies, those have been successful studies in general. So an enhanced fraction of Lyman break galaxies constrained by broadband photometry would indicate enhanced star formation in another way. So looking at relatively unobscured galaxies. So we obtained HST imaging with WIFC3 and ACS down to an H-band magnitude limit of about 28, corresponding to normal star-forming galaxies, so not these extreme dust emitters. And we shrink that delta Z down to about 500 co-moving megaparsecs. So the redshift constraints are better than having absolutely none. Of course, we're using broadband here to, get as much light as possible. And then there are follow-up options to get very secure redshift estimates, but we can definitely get pretty far this way. So we are looking for V or I band dropouts to get to redshift 6 or 7. And then we also have the parallel fields with HST, and those are about 2 megaparsecs away. So they might either represent the field, giving us a nice control sample to compare to, or it could be further evidence of filamentary structure if we also find overdensities in those somewhat nearby fields. So here we are using, as a first pass, these color cuts that have been used for UV luminosity function papers. So the actual sample that we are looking at is 3 of the original 35 quasars that had more than one ALMA continuum source, suggesting perhaps a local overdensity. And then we, again, impose these color cuts according to typical spectra of LBGs, of varying UV betas. And this is following the criteria that was used in the Buins and the Finkelstein papers for the redshift 6 and 7 UV luminosity functions. So I'm showing one of those color plots here, where the blue points are the sources in one of the quasar fields with an H-band signal to noise greater than 5, and plotting all the way down to signal to noise of redshift 3, signal to noise cut of 3.5. And then the shaded regions are those color criteria for the redshift 6 and the redshift 7 UV luminosity functions. There's a pretty well-defined region where we would expect the high redshift LBGs to sit. The green crosses are showing typical colors of brown dwarfs, which might concern you as a source of contamination. However, they are much brighter than a very high redshift galaxy. Even though they are faint stars, they're still much brighter than a typical high redshift galaxy by several orders of magnitude. So that's not a huge concern here. I'm showing on the bottom here an example of one of these dropouts, which seems like encouraging evidence for an LBG. But here I'm showing that there's significant uncertainty in the color space. And the error bars are coming from taking these template LBGs and allowing the individual photometry points to vary within 1 sigma of the actual noise in our images. And the color can have pretty profound differences. And so we see that real LBGs will move in and out of this in this color space, especially for very red betas. And so we would definitely want a more robust way of constraining these. And that would be with photometric redshift fitting. So I'll get to that in a moment. But just using these color criteria, assuming that that is a well-defined color region because it has been, successful for these blank field UV luminosity functions, I want to compare to those directly. So in a WFC3 pointing with a redshift accuracy, basically delta Z of 1, we would expect 30 to 50 LBGs at a brightness of minus 18.5 in the blank field. So that is the Finkelstein et al. 2015 UV luminosity function. So the cyan points are showing the parallel fields, and then the magenta points are the quasar fields. So preliminary results suggest that quasar fields are pretty much indistinguishable from the field for most of the UV luminosity function, except for the bright end. There is a very different slope there. And so that is encouraging evidence for very specific enhanced galaxy evolution, namely in the most massive ones. But again, we don't have really strong constraints just yet. So these are fairly preliminary results. So I mentioned that SED fitting would be the next steps. And so I've been using EASY and MagFizz to try to fit those galaxies, the candidate galaxies that I presented before. So ideally, we would get much more robust redshift estimates. These photometric, these SED fitters are very successful for lots of samples of galaxies. So we have HST photometry. There's also Spitzer imaging in all of these fields. However, there are important degeneracies at play for specifically this redshift region. So both MagFizz and EASY, well, any SED fitter is going to be sensitive to the templates that you provide it. But again, most MagFizz and EASY results for many of these galaxies result in low redshift solutions, which and maybe you think that indeed most of these galaxies are at low redshift, but even when we feed it mock photometry from LBG spectra that are definitely at redshift 6, we are still finding these low redshift solutions. So that probably means that we need a better template for LBGs at this redshift. It's possible that we can't use lower redshift templates and simply, move them in wavelength space, because it's possible that they have different physical properties. Some have suggested that Lyman alpha attenuation from the IGM is a much more important effect at redshift 6 or 7. And so that could be one reason why these fits are failing, or, just not returning what we might expect. So I'm showing you here mock photometry that is coming directly from a template LBG of 2 different slopes. One correctly identifies it at redshift 6, and then one thinks it's at redshift 1.3. So this is very preliminary ongoing work. But to finally wrap this up with some cosmological context, SAM predictions of redshift 4 and 5 LBGs show that brighter LBGs are more strongly clustered and in turn reside in more massive halos. And that could be what we are seeing here if indeed we are seeing an enhancement of more massive galaxies. And then on the right, I'm showing results from blank field UV luminosity function studies that find that the slope and the peak of the redshift evolution of star-forming galaxies are different between a faint and a bright subset of the population. So I would be very interested to know, knowing that we are probing from a redshift 6, 6.5, and 7 quasar, if we can, compare to this relation. So very, very preliminarily separating the cyan, which are the parallels, and again, the magenta being the quasar fields, we see that perhaps they are different from the blank field predictions. But I don't have errors here. This is very first pass, just kind of estimating. We see that there may indeed be an enhancement of the brighter galaxies, especially at the higher redshifts. And there could even be a different evolution of the fainter galaxies as well. So again, very preliminary results, but encouraging that we might be finding something different from the blank field. So in summary, quasars at high redshift, particularly redshifts greater than 4, can trace mass overdensities, which allows us to form an evolutionary link between the early signatures of protoclusters and modern day galaxy clusters. So in my new study, we are using Lyman alpha as a complementary search tool for my previous work in using millimeter dust, continuum, or other people's work that has used ISM tracers like C+. So we're looking for star-forming galaxies and trying to better constrain their redshifts near quasars, and comparing the population of LBGs that we find with the original sources that we had found in continuum in the millimeter. So the result of my master's thesis from 2018 was that there was no millimeter continuum flux overdensity, but we are using HST broadband data to look for LBG dropouts in 3 overdense quasar fields. So still to come are fitting photometric redshifts, which will help constrain the luminosity functions to better than a delta C of 1, dependent on the templates that we use. So getting a photometric redshift would definitely improve this beyond just using a simple dropout criterion, but this is still a work in progress. And then finally, calculating the angular correlation between the quasar and what we consider to be confirmed LBGs will help constrain the spatial strength of these potential overdensities and allow us to compare to other studies looking at the autocorrelation and of LBGs, as well as comparing them to the QSOs themselves. So thank you for listening and for watching my awkward pre-recorded talk, please feel free to email me at jchampagne@utexas.edu if you would like to talk to me further. I had also listed my Twitter in the beginning, which is at whatamerger jr. So I'm excited to talk to you all during the conference, or if you are just a casual viewer, again, thank you for listening. And I look forward to talking with you in the future. And now I have to find the stop recording button, which is somewhere indeed. There we go. Goodbye.